Hello everyone. Yesterday we had just started off with definition of turbulence, decomposition of mean flow and fluctuating components. Expressions for mean flow and fluctuating components were given, and we had Reynolds averaged the conservation of mass and momentum. So today we will do conservation of energy. Before I do that, so let's just take a quick look of these are the governing equations which had no simplifications, that is conservation of mass, 3 momentum and 1 energy. Now the left hand side is the inertia force, this is the pressure force, these are the viscous forces, and Fx is the body force. So now du by dt is the total acceleration, that is del u by del t plus u del u by del x plus v del u by del y plus w del u by del z. Now if I take incompressible flow, this term, that is mu by 3 del u by del x plus del v by del y plus del w by del z, will become 0. So then this is the conservation of energy. So you have the total derivative of temperature on the left hand side, which is the convection term, and then the conduction term, pressure work and viscous dissipation. Pressure work and viscous dissipation get neglected if we consider the incompressible flow. So we end up with only the rho Cp dt dt and k del square t by del x squared plus del square t by del y squared plus del square t by del z squared. So we said, okay, this is the Reynolds experiment where we said that the 2100 is the critical Reynolds number, and I just showed you the video about the dissipation of the eddies downstream a circular cylinder and the trapezoidal cylinder, and I gave you the desirable situations of turbulent and the laminar flow. And this was the definition of the turbulence which was given by Taylor and von Karman, which said that turbulent motion can be considered as an irregular condition of flow in which various quantities show a random variation with time and space, which enables us to give the statistically distinct average values. So then we decomposed the motion into mean motion and the fluctuating motion, that is u equal to u bar plus u prime, and u bar definition is 1 by t integral of u dt within the limits t naught to t naught plus t, and we found that u prime bar is equal to 0, so it doesn't help us. So we defined, to quantify the fluctuating component, we squared it and then averaged it, that is u prime squared bar. It is kind of standard deviation if I have to tell you. So u prime squared bar exists, and then we define turbulence intensity as the square root of u prime squared bar upon u bar into 100, that is the turbulence intensity, and we derived relations for uv, and these were the rules which were stated without derivations. We took the incompressible flow continuity equation and the x momentum equation, and we time averaged the continuity equation. We got del u bar by del x plus del v bar by del y plus del w bar by del z equal to 0, and then we did the Reynolds averaging of the momentum equation by rearranging this equation, and we got that del u by del t equal to 0 because we are considering mean steady flow, and then we Reynolds averaged term by term, that is we took del u squared bar by del x, del uv bar by del y and del uw bar by del z, and we found that we got the extra terms, that is del u bar squared by del x, del u prime v prime bar by del y and del u prime w prime bar by del z. Similarly for pressure we got del p bar by del x, and for mu del squared u bar by del x squared, del squared u bar by del y squared, del squared u bar by del z squared. So similarly we extended this for the x, the y and the z momentum equation. So you have these additional terms, we pushed it to the right hand side. These 9 additional terms can be visualized as the extra normal and turbulent stresses. So these are the equations which you get, but by Reynolds averaging. So without Reynolds averaging, these were the terms we had. So these stresses are the 3 normal stresses, that is minus rho u prime squared bar, minus rho v prime squared bar, minus rho w prime squared bar, and shear stresses as minus rho u prime v prime bar, minus rho v prime w prime bar, minus rho u prime w prime bar. So then these are the additional stresses which are called as Reynolds stresses. So these stresses, we said that although they are appearing with negative, positive u prime induces negative v prime and negative v prime induces positive u prime. So you get tau xy actually as positive. So this is over and above our viscous shear stress, that is mu del u bar by del y. So this was the physical significance of the turbulent stresses, and then we said that the total shear stress is equal to tau laminar plus tau turbulent. So that is mu del u by del y minus rho u prime v prime bar. So in laminar boundary layer you have minus rho u prime v prime bar as 0 because u prime is 0 and v prime is 0. So then we introduced a universal velocity profile, and we said that there are 3 layers: viscous sublayer, overlap layer and outer layer. This is the flow in a pipe. So viscous sublayer laminar shear stress is larger than turbulent shear stress, and overlap layer both laminar and turbulent shear stresses are of the same order, and in the turbulent layer laminar shear stress is lower than that of the turbulent shear stress, or turbulent shear stress is greater than that of the laminar shear stress. So then we said the viscous sublayer can be represented with u plus equal to y plus less than 5, and overlap layer u plus equal to 5 log of y plus minus 3.05, y plus between 5 to 30, and turbulent layer is u plus equal to 2.5 log of y plus 5.5 for y plus greater than 30, and u plus is nothing but u by u tau. U tau is frictional velocity. We showed yesterday that the unit of the u tau reduces to meters per second, and y plus is y u tau by nu. We showed that this is non-dimensional. So this is called universal velocity profile. Why it is called universal? Because it is valid not just for external flows but also for internal flows. However, it is not valid for jet flows. We need to remember that this is only valid for internal and external flows. So this is kind of semi-empirical. If you compare that viscous sublayer and the buffer layer and the turbulent layer, they are all matching with the experimental data. Today in one of the modules we are going to derive that these u plus or the universal velocity profile. So now let us do the time averaging of back to writing time averaging of energy equation. So for incompressible flow, my energy equation is, if I just see the slides, this is my energy equation. So this is the convection term, conduction term, pressure work term, viscous dissipation, volumetric heat generation. I am considering incompressible because of which dP by dt is equal to 0 and the viscous dissipation is 0, and I am neglecting the volumetric generation. So I am having only this total derivative of temperature and the conduction term. So let us write that rho Cp del T by del T plus U del T by del X plus V del T by del Y plus W del T by del Z is equal to K into del squared T by del X squared plus del squared T by del Y squared plus del squared T by del Z squared. Like we did in the momentum equation, we shall rearrange the left hand side so that time averaging becomes easy. So rho Cp del T by del T plus del of ut by del x plus del of vt by del y plus del of wt by del z is equal to k del squared t by del x squared plus del squared t by del y squared plus del squared t by del z squared. So if I show the slides, if I just come back to slides, if I expand this, you get the total derivative of t, and you get t plus del u by del x plus del v by del y plus del w by del z. This term gets 0 because by continuity, because we are considering incompressible flow. So this is the same as what we have written in the top. So if I take if I come back to my writing, so we will replace for time averaging t by t bar plus t prime and u as u bar plus u prime and v as v bar plus v prime and w as w bar plus w prime. So if I come back to slides, so what is that I have just replaced here? Del of t bar plus t prime bar and del of u bar plus u prime bar, t bar plus t prime bar, so on and so forth. So let us take up each term and see how it gets time average. So first term, del of t bar plus t prime bar by del t equal to del t bar by del t plus del t prime bar by del t. This is 0, this del t bar by del t can be neglected because t prime bar equal to 0. So you get del t bar by del t. So now next term, del of u bar plus u prime into t bar plus t prime bar upon del x. So you get del of u bar t bar plus u prime t bar plus t prime u bar plus u prime t prime bar upon del x. As I have shown yesterday, this term will be 0 because u prime bar is 0. This term will be 0 because t prime bar is 0. So you get del of u prime t bar upon del x plus del of u prime t prime bar upon del x, that is nothing but u bar del t bar by del x plus t bar del u bar by del x plus del u prime t prime bar upon del x. This is my del u bar plus u prime t bar plus t prime bar upon del x. So I have found del of t bar plus t prime as this first term, and this is my second term. Okay, now let us take up the third term. Third term I can directly write, that is del of v bar plus v prime into t bar plus t prime bar upon del y is equal to v bar del t bar by del y plus t bar del v bar by del y plus del of v prime t prime bar upon del y. Del of next term w bar plus w prime t bar plus t prime bar upon del y is equal to w bar del t bar by del y plus t bar del w bar by del y plus del w prime t prime bar by del, this is not del y, this is del z, del z, del z, del z. Now the right hand terms, you have del squared t bar plus t prime bar by del x squared, you get del squared t bar by del x squared plus del squared t prime bar by del x squared. So this is 0 because t prime bar is 0. So you end up getting del squared t bar plus t prime is equal to del squared t bar by del x squared. Similarly, del squared t bar plus t prime by bar by del y squared equal to del squared t bar by del y squared and del squared t bar plus t prime bar upon del z squared is equal to del squared t bar by del z squared. So just if you see the slides here for a minute, back to slides, if I see the slides, each term I have written here, each of these terms I have expanded and written. So if we substitute all of this, let's substitute all of this into my energy equation. So I get rho Cp into, or I can put, okay, let's write rho Cp into del T bar by del T plus you have U bar del T bar by del X. Okay, I have two terms here, that is U bar del T bar by del X plus T bar del U bar by del X. I am taking T bar common and write del U bar by del X plus del of U prime T prime bar upon del X plus V bar del T bar by del Y plus T bar del V bar by del Y plus here plus del V prime T prime bar by del Y plus W bar del T bar by del Z plus T bar del W bar by del Z plus del by del Z of W prime T prime bar is equal to K del squared T bar by del X squared plus del squared T bar by del Y squared plus del squared T bar by del Z squared. So you can notice that this is nothing but my continuity equation. So this is 0 by continuity, 0 by continuity. So my energy equation reduces to, I will push all these turbulence parameters to the right hand side like I did in momentum equation. So U bar del T bar by del, and also another thing what I am doing is I am considering mean steady flow. So for mean steady flow, del T bar by del T is 0. So I can neglect this and I will push this rho Cp to the right hand side. So I get U bar del T bar by del X plus V bar del T bar by del Y plus W bar del T bar by del Z is equal to alpha del squared T bar by del X squared plus del squared T bar by del Y squared plus del squared T bar by del Z squared minus, because I am pushing this on the right hand side, so del U prime T prime bar by del X, if I take minus as common, plus del V prime T prime bar by del Y plus del of W prime T prime bar by del Z. You see, these were the terms earlier which were there, but now this is the additional stresses. You can think of additional stresses which are going to aid, like turbulent shear stress. These are going to get additional heat flux. They are going to contribute for additional heat flux. So if I come to slides here, for a minute, so here this is what I have written. So this is the mean terms, this is the mean term, this is the fluctuating term. So now if I go to the next slide, this is the closure problem. I don't intend to write these equations here, I just want to see here. So you see, this is, you have continuity equation. Remember, this we have written for incompressible flows. This is for incompressible. This is my continuity equation and this is my momentum equation X, and this is Y momentum equation, Z momentum equation and the energy equation. So total how many equations I have? I have total 5 equations. And how many unknowns I have? U bar, V bar, W bar, P bar, T bar, and now you see the slides 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All derivatives of the fluctuating components, both velocity and temperature as products. So that means 5 plus 12, so that is 17 unknowns are there. How many equations? Only 5 equations. So this is what, because it's not a closed problem. So this is why it is called closure problem. That is why this is called as closure problem. So if I see here, again back to my slides, we have 5 equations, 17 unknowns. The unknowns are u bar, v bar, w bar, p bar and t bar, and 12 terms of the type del by del y of u prime v prime bar, hence the closure problem. Fortunately, the gap between the equations and the unknowns is not so menacing, because if we consider a few simple flow configurations such as boundary layers and fully developed flow through straight ducts, we can get slightly closed form solutions. So what we shall do is, now we shall write the boundary layer equations. So let's write the boundary layer equations. So if I take the continuity equations, so in the boundary, so let us write down boundary layer equations. So the next topic which we are starting is boundary layer equations. So in this boundary layer equations, what is that we are considering is, we are considering, if we just get to slides here, considering turbulent flow near a wall parallel to a free stream u infinity and t infinity oriented in the positive x direction, that is flow over a flat plate. So turbulent flow, we are considering turbulent flow with velocity u infinity, t infinity in positive x direction. Now, although the actual turbulent flow is 3-dimensional, from symmetry, the terms representing del by del z, we will consider that del by del z terms vanish, do not exist. Next is, as in laminar flow, we consider y momentum equation can be neglected. Y momentum equation is neglected. We have argued this during boundary layer equations in laminar. If you get doubt, please, I would request you to revisit those modules and get yourself convinced why y momentum equation is neglected. And z momentum does not exist. Z momentum does not exist. So with this, what will I get? So the continuity equation would be del u bar by del x plus del v bar by del y equal to 0. That is my continuity equation. Now, the next thing is, if we just take the momentum equation which we have derived in the, if we just go to the previous slide, here you see in the left hand side your w bar is not there and del by del z term is not there. So you get u bar del u bar by del x plus v bar del u bar by del y equal to, you see this pressure term would be there, okay, that is minus 1 by rho del p bar by del x plus, now you see among the viscous terms x and z, z doesn't exist, the scale of the x, is greater than the scale of the z. So you get only nu del squared u bar by del y squared. This we have done in boundary layer equations. Similarly, we say that del u prime v prime bar upon del y is greater than del u prime squared bar by del x. Del by del z term is not there. So I get only plus minus of del of u prime v prime bar upon del y. Now let us take up the energy equation. This is what we had written, the energy equation, time averaged. Here you see this W bar doesn't exist and del T bar by del Z doesn't exist. So on the left hand side you have only U bar del T bar by del X plus V bar del T bar by del Y. Let's write that. You get U bar del T bar by del X plus V bar del T bar by del Y is equal to, now let us take up this here again, alpha del squared T bar by del X squared del squared T bar by del Y squared. You see here, X is of the scale of L and Y is of the scale of delta. This is what we had taken. So our delta T. So delta T is very much smaller than L. So this term will vanish and only this term will be there, and del by del Z term anyway is not there. So you have alpha del squared T bar by del Z squared minus of, now we have three terms. Out of these terms, three terms, del by del Z term is not there. Out of these two terms again, this is smaller than this, that is del of U prime T prime bar upon del X is less than del of V prime T prime bar upon del Y. So I will be left out with only del of V prime T prime bar upon del Y. Okay. So if I get back to slides, these are the three equations which I have gotten, and these we are writing as, these are my boundary layer equations. Okay. Yes, del Y squared. There is a typo here. Please correct it. This is, sorry, this is del Y. This is del Y squared. This is correct. If you get to the slides, what I have written here is wrong. So here this is del squared T bar by del Y squared minus del V bar V prime T prime bar by del Y. Now this is now I am going to introduce something called eddy diffusivity, momentum and thermal diffusivity. That is, now let us write these equations little differently. So I will focus only on, let's write del U bar by del X plus del V bar by del Y equal to 0, continuity is over. The momentum is U bar del U bar by del X plus V bar del U bar by del Y equal to minus of 1 by rho del P bar by del X plus, you see in this equation what I am doing is, I am taking 1 by rho del by del Y of, I am writing. So 1 by rho del by del Y into mu del U bar by del Y minus of rho U prime V prime bar. Okay. Similarly, the energy equation, U bar del T bar by del X plus V bar del T bar by del Y is equal to 1 by rho Cp del by del Y of K del T bar by del Y minus rho Cp V prime T prime bar. V prime T prime bar. Now I define what is called eddy shear stress. Eddy shear stress, that is minus rho U prime V prime bar. You see here mu del U bar del Y can be, is a shear stress. So minus rho U prime V prime bar, I am calling it as one more shear stress, that is eddy shear stress, which is equal to rho epsilon m del U bar by del Y, where epsilon m is eddy momentum diffusivity. This is a bold assumption. Why do I call this as bold? Because the fluctuating components we are representing in terms of the mean components, and defining one more diffusivity, that is nu as kinematic viscosity is a momentum diffusivity. See, here also we are defining as turbulent momentum diffusivity or eddy momentum diffusivity, that is epsilon m. So now we can define eddy heat flux. Let's write eddy heat flux. Eddy heat flux, that is minus rho Cp V prime T prime bar is equal to rho Cp epsilon H del T bar by del Y, where epsilon H is eddy thermal diffusivity. If I substitute this in these equations, so what do I get? Del U bar by del X plus del V bar by del Y equal to 0, and U bar del U bar by del X plus V bar del U bar by del Y equal to minus 1 by rho del P bar by del X plus del by del Y. I am pushing rho inside, so I get nu plus epsilon m into del U bar by del Y. And similarly, energy equation, U bar del T bar by del X plus V bar del T bar by del Y is equal to del by del Y of rho Cp I am pushing inside. So I get alpha plus epsilon H del T bar by del Y. Del T bar by del Y. Remember, epsilon m and epsilon H, unlike nu and alpha, are not properties of fluid but properties of flow. Nu and alpha were properties of fluid. That is the major difference. Flow means whether it depends on the internal flow or external flow, it depends on that. So this epsilon m, we will come to how do we get these values of epsilon m and epsilon H. So if I come back to slides, so these are the equations which I had, and now if you see, my life has not become any better, because what are the unknowns still? I have U bar, V bar, P bar, T bar, epsilon m, epsilon H. So I have 6 unknowns, and equations are still 3 only. Okay. So how to close these equations is what is termed as turbulence modeling. Turbulence modeling. So this is epsilon m and epsilon H. Epsilon m and epsilon H are based on the empirical data. So this is where we will stop and continue this in the next module.